Welcome to Boring Lectures, the podcast designed to help you fall asleep. We know sleep doesn't always come easily. That's why we're here. Each episode, we take genuinely interesting scientific topics and present them in a deliberately and delightfully dull way. We explore them slowly, methodically, with soothing repetition and gentle monotony, all so you can relax and drift peacefully off to sleep. Tonight, we'll be discussing the history and mechanics of elevators. We'll move through the topic calmly, without drama, covering every detail at a pace that invites rest. If you'd like more calm lectures like this, you can follow Boring Lectures in your podcast app. And, when you're not about to fall asleep, leave a rating or review. It quietly helps the show reach others who might need a gentle way to drift off. For now, settle into a comfortable position. Adjust your pillow. When you're ready, you can close your eyes or simply soften your gaze. We hope you're bored to sleep. Let us begin our methodical examination of the history and mechanics of elevators. We shall proceed through this topic in a careful, deliberate manner, considering each element in turn. The elevator stands as one of the most significant technological achievements in human history. It has fundamentally transformed the way people inhabit buildings and organize urban spaces. The development of safe, reliable elevator systems from the mid-19th century onward enabled the construction of tall buildings that would otherwise remain impractical for human occupancy. This reshaping of skylines across the world established the vertical cities that characterize modern metropolitan areas. The history of the elevator extends far deeper into the past than many realize. Its origins are traceable to ancient civilizations that employed basic hoisting mechanisms for moving materials vertically. However, the modern elevator as a practical system for transporting passengers safely through buildings emerged during the 19th century. This was a period characterized by rapid industrialization, urban growth, and mechanical innovation. The earliest documented attempts to create mechanical lifting devices date back centuries. But the technological breakthroughs that enabled practical passenger elevators occurred during a remarkably compressed historical period. This period spanned only a few decades in the middle of the 1800s. Let us now consider the foundational work in wire rope technology. In 1827, Wilhelm August Julius Albert performed the first tests upon iron wire rope. He established the material properties and performance characteristics that would eventually make practical, cable-driven elevators feasible. This seemingly technical innovation provided the necessary foundation for subsequent developments. Wire rope possessed superior strength-to-weight ratios compared to earlier hoisting materials. It demonstrated greater reliability under repeated loading cycles. The strength and durability of wire rope would prove essential for systems designed to operate continuously throughout the day. Shortly after the establishment of wire rope as a viable lifting medium, additional mechanical innovations began to accumulate. In 1829, American physicist John Henry constructed an early version of the electromagnetic motor. This established the feasibility of powered mechanical movement. This development would eventually enable motorized elevators, rather than relying exclusively on steam power or human operation. During this same period of rapid innovation, in 1833, Burgomaster Durell of Clausthal in the Harz Mountains developed a system. In this system, men were raised and lowered by reciprocating rods extending the length of mine shafts. Initial tests demonstrated the capability to achieve heights up to approximately 200 meters. Subsequent refinement allowed the depth to reach about 420 meters. These mining elevator systems, though primitive by modern standards, demonstrated an important principle. They showed that vertical transportation over substantial distances could be engineered and operated with reasonable reliability. The development trajectory continued during the 1850s with increasingly sophisticated innovations. These innovations addressed specific technical challenges. In 1850, Henry Waterman of New York City was credited with inventing standing rope control. This system represented an important advancement in the mechanical governance of elevator movement. The following year, in 1851, George Fox and Company of Boston introduced the idea of self-locking worm gear. This was used to drive an elevator drum hoist. It provided a mechanical solution to the problem of preventing the elevator car from descending when power was removed. This self-locking mechanism represented a crucial safety innovation. It addressed one of the fundamental dangers inherent in any powered lifting system. The year 1851 also witnessed another significant innovation in hydraulic elevator systems. To remedy insufficient water pressure from city water mains, Sir William Armstrong developed the first accumulator. In this instance, it was a large diameter vertical piston supporting a huge wrought iron bucket filled with stones. The weight of the bucket, load, and piston upon the water a steam engine had pumped into the accumulator assured a steady supply of pressure. This pressure could be as much as 700 pounds per square inch. This hydraulic innovation would later provide an alternative to cable-driven systems. It established one of the two fundamental approaches to elevator mechanical design that persist to the present day. Moving methodically to the most pivotal moment in elevator history. This occurred in 1854 when Elisha Graves Otis demonstrated the first safety elevator. The demonstration took place at the New York Exposition in the Crystal Palace. This demonstration proved that elevator travel for passengers was safe. Elisha Graves Otis was born August 3, 1811, in Halifax, Vermont. He was an American industrialist and founder of the Otis Elevator Company. He revolutionized vertical transportation through his invention of a critical safety mechanism. In 1853, while working at the Mays and Burns bedstead factory in Yonkers, New York, Otis invented a safety device. This device prevents elevators from falling if the hoisting cable fails. The factory needed a hoist to lift heavy equipment to the upper floor, but this posed serious safety issues. Otis responded to this practical challenge with his groundbreaking invention. The demonstration at the Crystal Palace proved to be extraordinarily effective. It established public confidence in elevator technology. Following this public demonstration of his new invention at the New York Crystal Palace in 1854, demand for the safety elevator began to rise. Otis established the Otis Elevator Company in 1853, following the invention of the safety elevator. Although the company initially focused on freight elevators, having only made freight elevators since 1853 when they opened, the company received its first order for a passenger elevator in 1857. On March 23, 1857, Otis installed the first safety elevator for passenger service. This was in the store of E.V. Hawout and Company in New York City. This established a landmark in the history of vertical transportation. The establishment of the Otis Elevator Company and successful deployment of the first passenger safety elevator in 1857 marked the beginning of the commercial elevator industry. Following this critical milestone, the pace of technological innovation accelerated considerably. Numerous inventors and engineers contributed incremental but collectively significant improvements to elevator systems. In 1856, William H. Thompson and Eustace P. Morgan patented their safety hatch for warehouses. This was a system of sliding or hinged hatch doors placed in the opening of each floor. It reduced the spread of fire and prevented unauthorized access to elevator shafts. The period between 1860 and 1880 witnessed the emergence of diverse elevator systems. These systems reflected different mechanical philosophies and addressed particular operational requirements. In 1862, the first funicular railway was built by Frenchmen Molinos and Pronier in Croix-Rousse, Lyon. Its slope was 16 degrees and travel distance was 1,530 feet. This established another form of mechanical vertical transportation. The year 1863 witnessed two significant developments. Baker Street Station opened, and London became the first city to develop an underground railway, which is a subway. Also, William Miller patented the first elevator using worm rack integral with car platform for lifting and preventing fall of car. In 1867, Campbell Whittier and Company began production of the Miller patent screw lift machine. These had capacities ranging from 2,000 to 8,000 pounds. This established commercial production of this elevator design. During this same period, hydraulic elevator systems were rapidly advancing as an alternative to cable-driven mechanisms. In 1867, Léon Aidou displayed at the Universal Paris exhibition the first secure direct-action hydraulic elevators. These carried visitors to an observation platform 65 feet high. The 4 hollow cast-iron columns guiding the lift also served as containers for 4 counterweights. These were attached to chains that ran over sheaves down to the car, making the passengers secure. In 1868, Otis Brothers patented its own variation of the worm-driven drum. Waygood manufactured its first hydraulic elevator. Richard Waygood had founded the company in 1842. During this same year in 1868, construction of the New York City subway started. This required vertical transportation systems for accessing underground stations. The year 1869 witnessed another hydraulic innovation. William E. Hale patented and introduced the Hale water balance elevator in Chicago. Its novelty consisted of using the force of gravity for its operation. This approach represented a different philosophical approach to hydraulic elevators compared to conventional pump-driven systems. The year 1872 brought several important innovations. Timothy Stebbins designed and patented a rack and pinion machine driven by a vertical hydraulic piston. It had the ability to modify carrying capacity and speed by changing gear size. The first vertical geared hydraulic elevator was installed in New York City during 1872. German engineers Nicholas August Otto and Eugene Langen began marketing a 2-cycle gas engine in 1872. Though while 5,000 were sold, its size allowed use only at a permanent site. This limited its application to elevators. The development of electric elevators represented perhaps the most significant technological transition in elevator history. In 1878, the first electric elevator was built by Siemens in Mannheim, Germany. A patent was issued the same year to Siemens and Halske. The advent of electric motors provided advantages over steam power. These included improved control, reduced maintenance, cleaner operation, and the ability to be located throughout a building. This was rather than requiring central boiler facilities. In 1878, Charles Hill Morgan patented a direct-action hydraulic elevator. He installed the first such type in the Washburn and Moore Wire Works in Worcester, Massachusetts. The final decades of the 19th century witnessed the consolidation of elevator technology. There was the emergence of dominant manufacturers and system types. The year 1880 marked the installation of a small tramway in a tunnel under the intervening Hôtel du Louvre in Paris. This connected separate stores of the Grand Magasin du Louvre. Cabins were placed on the interior railway by hydraulic elevators. In 1889, Otis produced the first alternating current-operated elevator in New York City. This represented the transition from direct current to alternating current electrical power systems. This same year witnessed Amiot introducing his curved staircase private elevator at the Paris Universal Exhibition. This demonstrated the adaptability of elevator technology to diverse architectural configurations. The year 1890 witnessed de Buren, a Frenchman, installing what is said to have been the first gearless elevator. This was in New York City's German-American House. This established the gearless traction design that would eventually dominate modern elevator systems. Let us now turn our attention to the classification and categorization of elevator types. The diversity of elevator applications and building requirements has necessitated the development of multiple elevator types. Each type is optimized for particular transportation purposes, passenger loads, and operational environments. These classifications represent systematic approaches to matching elevator design with specific functional requirements. This ensures that each installation provides appropriate capacity, speed, and features for its intended use. The primary classification of elevators distinguishes between passenger elevators, service elevators, freight elevators, and dumbwaiters. Each category serves distinctly different transportation functions. Each is subject to particular regulatory requirements. A passenger elevator is any elevator intended for the transport of people through a building. These elevators can vary drastically in terms of size, speed, and interior options depending on the use of the elevator. Passenger elevators form the most common elevator type. They are deployed in virtually all multi-story residential and commercial buildings. These elevators are designed with passenger comfort as a primary consideration. They incorporate features such as decorative finishes, climate control, lighting, and audio systems. Passenger elevators typically operate at speeds ranging from moderate velocities in smaller buildings to very high speeds in tall buildings. The specific speed is determined by building height and expected passenger volume. A service elevator is found in many commercial buildings. It is intended for the transport of goods through the buildings by employees, such as the housekeeping staff moving cleaning carts through a hotel. Service elevators are also used in hospitals for the transport of patients on hospital beds. To comply with code requirements, service elevators are typically more robust and deeper than standard passenger elevators, so they can navigate larger items through the building. The design of service elevators emphasizes durability and load capacity, rather than aesthetic appeal. They have reinforced floors, protective wall padding, and simplified interior finishes. These facilitate frequent movement of large objects. A freight elevator is intended to move very heavy loads, such as cars or cargo, in industrial buildings. It is not intended for passenger transport. Freight elevators are designed to withstand tougher working conditions. Their interiors are focused on heavy steel walls and floors rather than more attractive options. These specialized systems may incorporate heavy-duty components throughout, including more robust cables, larger motors, and reinforced structural members to accommodate extreme loads. Freight elevators may be required to operate with extreme frequency in industrial settings. This necessitates exceptional durability and reliability. A dumbwaiter is a small freight elevator. It is often used for the transport of food in restaurants. However, dumbwaiters can be found in both commercial and private buildings. They provide convenient transport for small items between floors without occupying substantial floor space or requiring significant structural modifications. Dumbwaiters typically operate with modest load capacities, often in the range of several hundred pounds. They feature simplified control systems and compact designs that facilitate installation in existing buildings. Beyond classification by passenger or freight function, elevator systems are also classified based on their hoisting mechanism. This categorization reflects fundamental differences in mechanical design philosophy. Understanding these hoisting system classifications requires detailed examination of how various systems accomplish the basic elevator function. That is, raising and lowering a car through a vertical shaft. The two dominant hoisting system types employed in modern elevator installations are traction elevators and hydraulic elevators. Each represents distinct approaches to converting motor power into lifting force. These two system types differ fundamentally in their mechanical principles. They differ in performance characteristics, cost structures, maintenance requirements, and optimal applications. Traction elevators operate via a pulley system. They use steel ropes or belts and a counterweight to move the cabin up and down. The basic operational principle of traction elevators involves a drive sheave. This is a large wheel constructed with grooved surfaces designed to grip hoisting cables. The motor, through either direct drive in gearless systems or through gearing in geared systems, rotates this drive sheave. Steel hoisting cables pass over the drive sheave. One end is connected to the elevator car, and the other end is connected to a counterweight. As the drive sheave rotates, it propels the cables. This in turn raises or lowers the car and counterweight in opposite directions. The counterweight is specifically designed to balance the weight of the elevator car, plus approximately 40% of its rated load capacity. This results in a more balanced system that reduces motor strain and improves energy efficiency. Traction elevators exist in two primary variants: gearless traction and geared traction. Each offers distinct performance characteristics and optimal applications. Gearless traction elevators are the more advanced solution. They have a wheel attached directly to the motor. Counterweights are used to operate the hoisting system. In gearless systems, the drive sheave is integral with the motor's rotor. This eliminates the need for intermediate gearing. This direct connection enables higher speeds. It represents the culmination of more than a century of engineering refinement. Gearless traction elevators have a drive sheave that is directly attached to the end of the motor. They can reach speeds up to 2,000 feet per minute. The absence of gearing in these systems contributes to smoother operation. It contributes to reduced mechanical losses and lower maintenance requirements compared to geared alternatives. Gearless elevators can be more compact compared to geared elevator motors. This is mainly because they lack the gear components. In fact, gearless motors can be less than half the size of geared motors. This compact size is advantageous in terms of energy efficiency. Smaller motors require less electricity to operate. The absence of a gear unit reduces friction and, in turn, energy loss. Geared traction elevators use a gearbox to turn the hoisting sheave and lift the elevator. These systems are usually slower than gearless systems. In geared machines, the gearboxes are attached to the electric motor and turn the hoisting sheave and move the rope, whereas in the case of gearless elevators, the gearbox is attached directly to the motor. Geared traction elevators are powered by direct current or alternating current. The maximum speed of the geared traction lift is 500 feet per minute. On average, geared traction elevators can move up to the speed of 152 meters per minute. They can travel at a distance of up to 75 meters. Geared elevators require a machine room, whereas gearless elevators do not require a machine room. In order to mount geared elevators, the wheel, the motor, and a machine room need to be located above the elevator shaft, whereas in the case of the gearless elevators, the wheel is directly attached to the cabin. Thus, there is no requirement for the machine room. Geared traction elevators can be efficient in building up to 20 stories, but after that, the effect of the added weight of the gearbox becomes significant. The efficiency gains diminish. Gearless traction elevators are generally considered superior for tall buildings and high-speed applications. On the other hand, a gearless traction elevator can move at a speed of 610 meters per minute. It can travel at a maximum height of 600 meters. Despite this capability difference, both geared and gearless elevators have the same load capacity in terms of passenger weight. The motors on the gearless elevator make less vibration in the cabin while moving. They have a smoother stopping and moving function. This contributes towards a smoother and more comfortable elevator ride experience. When considering the aesthetic dimensions of elevators, compact and chic functional design of gearless traction elevators is often preferred. This is over the larger mechanical footprint of geared systems, particularly in modern buildings, emphasizing sleek architectural expression. Overall, traction elevators are typically more energy efficient. They provide a smoother and quieter ride for passengers. Most modern elevators are gearless traction. This is considered the most energy and space-efficient solution available. The energy consumption comparison between geared and gearless systems is particularly significant. Gearless elevators consume less amount of energy when compared to geared elevators. This is because there is no gear attached to the elevator. The gearless elevator is efficient, and the usage of electricity is less. As the motor gets smaller, and other components will also become smaller. This helps to solve the efficiency issue and make gearless motors more cost-effective. Hydraulic elevators represent an alternative hoisting system employing a fundamentally different mechanical principle. Hydraulic elevators are lifted by pistons from below. This type of hoist system is usually only used in low-rise buildings, typically up to 6 stories high, or to transport extremely heavy loads. Hydraulic elevators require more energy to operate than other elevator models. Due to the introduction of machine roomless elevators with high-efficiency machines and drives, they have largely been replaced in the elevator market. The operation of hydraulic elevators involves pressurized fluid forcing pistons upward. The extension of these pistons directly raises the elevator car. When pressurized fluid is released from the cylinders, the weight of the car and its contents causes a controlled descent. This occurs through a restricted orifice that regulates the descent speed. The advantages of hydraulic systems include their ability to handle extremely heavy loads and the smoothness of operation provided by fluid mechanics. Hydraulic systems are particularly suitable for specialized heavy load applications, such as freight elevators in industrial facilities or automotive service facilities where vehicles themselves must be transported between floors. However, the increasing energy consumption of hydraulic systems compared to modern traction systems has resulted in declining use, combined with environmental concerns regarding fluid disposal and the improved efficiency of machine roomless traction alternatives. This has resulted in declining use of hydraulic elevators for new installations. The typical capacity of an elevator is between 2,100 pounds to 5,000 pounds. While specialized lifts, such as freight elevators, can handle much higher loads, up to 20,000 pounds or more. Let us now examine the machine room and modern machine roomless elevator systems. The elevator hoisting mechanism and motor traditionally required a dedicated machine room. This was typically located either above the hoistway or at ground level, depending on system design. With advancing technology, it is no longer mandatory to have an elevator machine room to house the machine and drive components. This represents a significant departure from traditional elevator design. It reflects decades of engineering refinement focused on space efficiency in buildings. Machine roomless systems can be either traction or hydraulic. By incorporating more compact hoisting sheaves, they do not require a machine room to operate the lift. The machine is located directly in the elevator hoistway. This configuration provides the optimal use of space for the building design. Machine roomless designs have become increasingly popular in modern construction, particularly in buildings where available floor space is limited, or where architects prefer to dedicate all usable floor area to occupant functions rather than mechanical systems. By eliminating the machine room, developers can increase rentable or usable floor space. This offsets some of the costs associated with elevator modernization. Conversely, machine room systems can be either traction or hydraulic. In traction elevators, the machine room is typically located above the hoistway. This provides convenient access to mechanical components. It simplifies initial installation and maintenance procedures. However, the machine room can also be located at the bottom of the hoistway, or in a room adjacent to the elevator bank. This offers flexibility in mechanical room placement to accommodate building design constraints. The location of the machine room affects building layout. It affects structural design and the overall cost of elevator installation. Moving methodically to detailed mechanical components and systems. The transformation of electrical or hydraulic power into smooth, controlled, vertical movement requires the precise integration of numerous mechanical components. Each performs specific functions essential to overall system operation. Understanding these mechanical components requires detailed examination of their design, function, and interaction with other system elements. The hoistway forms the foundational structural element housing the entire elevator system. The hoistway is a critical component of any elevator system. It is the vertical shaft running through a building that houses the entire elevator system. The hoistway provides a safe and structured space for the elevator car, counterweight, guide rails, and other essential components to operate. The hoistway must be designed with precise dimensions, meeting building codes and manufacturer specifications. The internal dimensions determine the maximum size of the elevator car that can be accommodated. The hoistway structural integrity must be sufficient to support guide rail brackets, car and counterweight guide rails, and various safety equipment, all while maintaining dimensional accuracy throughout its height. The elevator car, or cabin, constitutes the space where passengers ride during vertical transportation. The elevator car, or cabin, is the space where passengers ride. It is designed to accommodate a specific weight limit. This is determined by the capacity of the hoisting cables and the motor. The car's design must also comply with safety regulations, including emergency exits, lighting, and communication systems. The internal dimensions of the car are determined by the hoistway dimensions and building code requirements specifying minimum clear space for passengers or freight. The car floor must be sufficiently robust to support the maximum rated load distributed across its surface. The car structure itself, including walls, ceiling, and safety devices mounted on the car roof, must be engineered to withstand operational stresses, while remaining as light as possible to minimize the load that must be supported by the hoisting cables. The hoisting cables, or ropes, constitute perhaps the most critical component in traction elevator systems. They are responsible for supporting the entire weight of the car and its contents. Hoisting cables are the strong steel ropes responsible for lifting and lowering the elevator car. They connect the car and counterweight to the hoisting machinery. The cables are designed to withstand significant tension. They are regularly inspected for safety. The specifications of elevator steel wire ropes are established by international standards. They are measured according to specific parameters including diameter, construction type, grade, lay, preforming, and core material. Elevator wire rope is specified by its diameter, construction, finish, grade, lay, preforming, and core. Diameter is expressed in inches or millimeters. It is the diameter of the circle formed by the extreme outer dimensions of the strands. New wire rope is manufactured to an oversized diameter of approximately 2.5%. This allows for the normal reduction of diameter experienced when a new rope is placed under load. The construction of elevator wire rope refers to the arrangement and number of strands and wires comprising the rope. Common constructions include 6 by 19 Warrington, 6 by 25 filler wire, 8 by 19 seal, and 8 by 25 filler wire configurations. The grade of wire rope refers to its tensile strength, typically measured in pounds per square inch, or in metric units as newtons per square millimeter. The lay of wire rope refers to the helical arrangement of wires within strands and strands within the rope, typically either right lay or left lay. Preforming and core material affect the properties of the rope. Different cores provide specific advantages for elevator applications. For conventional elevators, the traction rope recommended is the 8 by 19 construction, with sisal fiber core manufactured to meet specifications. The construction 8 by 19 refers to 8 strands of wire, each containing 19 individual wires. This provides a balanced combination of flexibility and strength, suitable for typical elevator applications. This construction has been proven through extensive use to provide excellent fatigue resistance. It complies with the highest international standards. The coating of wire rope is typically bright lubricated, galvanized on demand. This reduces corrosion and provides protective qualities. Specifications for elevator rope construction conform to ISO 4344 and ASMEA 17.6 standards. The diameter tolerance specifications for elevator wire rope are precisely defined to ensure proper operation with sheaves and drums. Diameter tolerance specifications indicate that at no load, the tolerance should be +2 to +5%, while at 10% minimum braking load, the tolerance should be 0 to +3%. These strict tolerances ensure that the rope maintains proper contact with sheave grooves and functions as designed. The minimum braking load specifications vary significantly based on the specific rope construction and grade. For example, traction rope with 8x19 construction and extra high-strength grade and various diameters provides the following nominal strength capabilities. A 3/8-inch diameter rope provides 9,000 to 11,000 pounds nominal strength. A 1/2-inch diameter provides 16,000 to 19,400 pounds. A 5/8-inch diameter provides 25,400 to 30,800 pounds. A 3/4-inch diameter provides 35,750 to 38,890 pounds. These progressively increasing load capacities with rope diameter enable selection of appropriate rope sizes for specific elevator applications. For high-performance wire ropes with 9x19 construction or similar, even greater strength capabilities are available. A 1/2-inch diameter provides 20,210 to 22,100 pounds nominal strength. The pulley system, or sheave assembly, works in tandem with the hoisting cables and motor to facilitate elevator operation. The pulley system, comprising sheaves or pulleys, works in tandem with the hoisting cables and motor. The pulleys, driven by the motor, facilitate the movement of the car along the guide rails. The system is designed to ensure efficient power transmission and smooth operation. The drive sheave represents the primary sheave engaged by the motor and responsible for propelling the hoisting cables. Guide sheaves, positioned at various locations within the hoistway, redirect the hoisting cables while supporting their weight and maintaining proper cable orientation. The specification of sheave dimensions requires careful calculation to ensure proper rope engagement and avoid excessive wear. The groove radius for sheaves is specified as a minimum of 0.53 to 0.535 times the rope diameter, with a maximum of 0.55 times the rope diameter. The groove depth is recommended to be approximately 1.5 times the rope diameter, or the rope diameter multiplied by the square root of 2. The sheave throat angle, which refers to the angle of the grooved surface, should normally use an angle of 35 to 45 degrees. Applications experiencing deflection angles greater than 1.5 degrees use 60-degree openings. Opening angles below 35 degrees are avoided. The sheave hardness must be minimum 35 RC, with better performance achieved at 40 to 45 RC. This provides adequate hardness to resist wear from rope contact. The counterweight represents a crucial component that balances the weight of the elevator car and its contents. The counterweight is a crucial component that balances the weight of the elevator car. It reduces the load on the motor, enhancing energy efficiency. The counterweight moves in the opposite direction to the car. This ensures the system remains balanced and stable. The counterweight is specifically designed to equal the weight of the empty car plus approximately 40 to 50% of its rated load capacity. This balancing creates an approximately equilibrated system where the net force required to raise or lower the car is minimized. This significantly reduces motor power requirements. Elevator cars are balanced by heavy counterweights that weigh the same amount as a car when it's loaded about 50%. This creates imagery similar to a seesaw. When the actual elevator goes up, the counterweight goes down. Or when the elevator goes down, the counterweight goes up. This helps put less strain on the cables. It makes the elevator safer to operate. The counterweight typically consists of a frame structure containing metal filler plates. Counterweight fillers are metal pieces stacked and bolted together within the counterweight frame to form the counterweight. When modernizing elevators or modifying car components that change the car's weight, new fillers may be required. This maintains the proper balance and maintains the 40% of the capacity load. The counterweight frame travels within its own set of guide rails. These are positioned parallel to the car's guide rails within the hoistway. The guide rails ensure precise alignment and smooth movement of both the car and counterweight. Guide rails are vertical rails located within the hoistway that guide the elevator car and counterweight. They ensure smooth and steady movement. They prevent any lateral motion. The guide rails are typically made of steel for durability and strength. Guide rails are T-shaped elevator components positioned throughout the elevator shaft. There are essentially vertical guides coming in two sets, one for the elevator car and another for the counterweight. Another rail's feature is a T-shaped cross-section with a level base and upright flanges. The size of the elevator guide rail depends on the size of the building and the elevator system itself. But usually there are standardized widths and heights. These range from approximately 3 inches or 75 millimeters to 12 inches or 300 millimeters in width, and 6 inches or 150 millimeters to 20 inches or 500 millimeters in height. These dimensions are not absolute and can vary significantly based on the elevator's load and capacity, as well as the general needs of the installation. One more thing that influences the size is the vertical distance the car needs to travel. Some tall buildings have guide rails going up several hundred feet. Local safety codes and regulations must be considered. Guide rails exist in multiple classifications reflecting their design and construction methodology. Solid elevator guide rail is made from a single piece of solid steel or aluminum. It is the most durable and reliable out of all three classifications. Solid guide rails are known for their immense strength. They are the #1 pick for elevators that need to carry heavy loads. These solid rails provide a stable base for the car to move on. The most special aspect of this rail is that they last for decades, so almost all high-rise buildings go for these. Hollow guide rails provide a lighter alternative while maintaining adequate strength. For mid-rise and residential buildings that don't require heavy load-carrying functionality, these rails balance structural integrity with practicality by being a reliable and efficient solution for a range of elevator applications. The weight per meter on hollow rail is less than its solid counterpart. Rollers or sliding shoes run along the guide rails, making the rolling mechanism for the elevator car and counterweight. They ensure that the elevator is aligned with the funnel at all times, and there's no swaying and tilting. The standard length of a single guide rail is 500 millimeters. The number of rails required for the elevator depends on the lifting height and pit depth. It can be calculated using the formula. Number of guide rails equals lifting height plus pit height multiplied by 2 divided by 500, with the result rounded upwards as the guide rails are to be used in their entirety. For example, with a lifting height of 3,000 millimeters and pit depth of 500 millimeters, the calculation process yields 3,000 plus 500 multiplied by 2 divided by 500 equals 14 pieces of guide rail. A special rule indicates that if the result is a small number, you need to add an additional one to ensure that the number of rails is sufficient. Installation of elevator guide rail is perhaps the most crucial aspect of elevator installation, as it has virtually zero margin for error. Only experts with years of experience perform this installation. As we examine in detail the remaining components, the traction machine, also known as the elevator machine, has a motor, drive sheave, brake, and machine bed plate. This helps pull the cabin up and down in an elevator that uses ropes. The motor of the traction machine moves the pulley shaft, so the cabin can move in the desired direction within the hoistway. This element should be maintained and checked regularly in case issues come up. The traction machine represents the mechanical heart of traction elevator systems, combining the motor, drive sheave, and braking systems into an integrated assembly that efficiently converts electrical power into controlled vertical movement. The buffer system provides critical safety protection in the event the elevator exceeds its intended lower limit. Buffers are energy-absorbing devices located at the bottom of the hoistway. They provide a crucial safety function by decelerating the car or counterweight in case of a fall. Buffers are designed to absorb the impact energy, preventing damage to the elevator system and ensuring passenger safety. Buffers act as a buffer, preventing possible accidents and injuries. These safety features are able to stop a descending car by controlling the kinetic energy of the elevator car. Elevator pit buffers are mechanical or hydraulic safety devices installed at the bottom of an elevator shaft. Their primary function is to absorb the impact if the elevator car or counterweight overshoots its intended travel limit. Acting as a cushioning mechanism, buffers help decelerate the car or counterweight gradually, minimizing damage and ensuring the safety of occupants. Two primary buffer types are employed in modern elevator systems. Spring buffers, made from coiled springs, compress when struck, absorbing energy. Spring buffers are commonly used in low-speed elevators with shorter travel distances. These buffers offer simple design, low maintenance, and cost-effectiveness. Hydraulic buffers use fluid to dampen the impact by forcing it through an orifice or channel to reduce speed. Hydraulic buffers are suitable for high-speed elevators and those with greater travel heights. These buffers provide better energy absorption for faster-moving systems, offering superior safety. The selection of buffer type depends on elevator operational speed. For low-speed elevators up to 200 feet per minute, spring buffers are commonly used for this speed range, providing sufficient energy absorption and being cost-effective for slower-moving elevator cars. For medium-speed elevators between 200 and 500 feet per minute, hydraulic buffers are typically employed. Hydraulic buffers are able to absorb greater impact forces, being ideal for mid-range elevator speeds. For high-speed elevators above 500 feet per minute, oil buffers are the standard for high-speed elevators, using oil to dissipate energy effectively, ensuring smoother deceleration and enhanced safety at higher velocities. The elevator pit is a recessed area at the bottom of the shaft that houses important components such as buffers, guide rail brackets, and space for maintenance technicians to safely perform inspections or repairs. It also acts as a safety zone if the elevator car travels beyond its lowest landing. The elevator pit is vulnerable to water intrusion, debris accumulation, rust, and corrosion, all of which can affect the entire elevator system, from electronics to structural parts. Regular maintenance of the elevator pit is not just a best practice, it's part of meeting local and national safety codes. A neglected pit can trigger inspection failures, costly repairs, or elevator shutdowns. The machine room, when used, provides housing for hoisting machinery, control systems, and electrical components. Machine room height should be 7 feet minimum, with proper lighting and switches to be provided by building systems. Proper ventilation is essential to maintain machine room temperature between 55 and 90 degrees Fahrenheit, with a maximum relative humidity of 85%. The machine room layout must accommodate equipment access and maintenance activities, while adhering to strict separation from occupied spaces to minimize noise transmission. This concludes our methodical examination of the history and mechanics of elevators. We have proceeded through the topic in a careful, deliberate manner, considering each element in turn, from the earliest wire rope innovations of 1827, through the safety demonstrations of Elisha Graves Otis in 1854, to the modern gearless traction systems and machine roomless configurations of today. We have examined the classifications of elevators, the mechanical components including hoisting cables, sheaves, counterweights, and guide rails, the buffer systems that provide safety protection, and the structural elements such as the hoistway and elevator pit. Each component performs its specific function, contributing to the safe and reliable vertical transportation that has become essential to modern building design. Thank you for spending part of your night with this episode of Boring Lectures. If this episode is helping you unwind, you might like to follow the podcast in your app. When you're rested, you can leave a short rating or review if you'd like. For now, just rest. Good night.